Okay, so we are starting to wind down here. We are in the home stretch of doing this calculation for an amphibole normalization. So the next step here, what we're going to want to do is calculate the oxide weights. And this, along with the site fillings, are the information that you would put into a paper. And so you would show all of the oxide weights here, you would show all the site fillings, and then the reader of your paper is going to know, that's the type of amphibole that you have, and we'll also get a feel for the quality of the analyses as well. So let's take a look at how this is calculated. It's really fairly straightforward. So why don't we start with the first column here, SiO2. Now, normally the way that these are set up is that they are ordered from the highest valence cation down to the lowest valence cation. And so that is how I'm going to set this up. Okay, so the way that this works is we are going to start with the raw moles of the element. And so the raw moles of SiO2, the raw moles of silicon is what we want to start with. So we go all the way back here. Okay, and there we have the raw moles of silicon. So I'm going to just kind of bring us back here for a moment. And what are we going to do with this? Well, how do we convert moles of silicon ultimately into weight percent of the oxide? Well, the first thing we need to do is we need a conversion factor. So we need to know how many moles of oxide are there per mole of the element. And so in silicon, or in SiO2, there is 1 mole of the oxide, so times 1, divided by 1 mole of the element. Okay, there is 1 Si per SiO2. Okay, and so it is 1 times 1 divided by 1. We'll see that factor changes a little bit for other oxides. And then we want to multiply this by the molecular weight of SiO2, and I've set the various molecular weights up here underneath the oxides in the same way that I had the atomic weights underneath the elements. And so I'm going to click on this. And again, we need a $sign here in front of the 3 because later on when we copy that down, we want to make sure that we stay in this row up here and that we don't accidentally start referencing rows that we are not expecting. So if I hit return here, we get a number of 51.3. So that looks pretty good. It's got way too many decimal places. We don't have that much precision in our analyses. And so I'm going to reduce this to 2 decimal places. We'll center it, and it looks pretty good. Okay, so what we can do now is I can do the same calculation here for titanium. I'm just going to copy it over here. Now I want to make sure that these are correct. So the Bn definitely is correct, and the 1 divided by 1 is correct because you can see that SiO2 and TiO2 are analogous formulas. But almost certainly this T8 is incorrect, so I'm going to go back up here to the beginning. I'm going to find titanium, and titanium is actually in the V column, so I'm going to change the T here to a V. Okay, now it doesn't change our value because we didn't have any titanium to start with, but nonetheless, we want to make sure that we do have the correct column that we're referencing. So now I'm going to do Al2O3, so I'm going to copy this again over here. And we have to make some corrections. So the first correction is going to be, well, let's make sure we have the aluminum column. So the aluminum column is not W, but in fact the aluminum column is R. So I'm going to change this to an R. Okay, so that's the first thing. But this number still isn't correct because we have 1 mole of aluminum oxide, but we actually have 2 moles of aluminum within a mole of aluminum oxide. And so this should actually be a 2 rather than a 1. Okay, and this will be the case for all of the oxides where it's, for example, Al2O3 or Fe2O3 or Na2O. Wherever you've got 2 of the cations, there's going to be a 2 in the denominator here. And so that reduces our 24 down to 12 and a little bit. Okay, so I'm going to momentarily skip iron because the calculation is a little different there, and I'm going to skip over to magnesium. Now, rather than copying the aluminum here, I'm going to copy the titanium cell, and I'm going to show you in a moment why I'm doing that. The reason that I'm doing that, of course, is because there is 1 titanium per TiO2, and there's 1 magnesium per MgO, and so this 1 divided by 1 stays the same. Okay, now you see we have an error message here. Well, that's because Z is not the correct column for magnesium, and so we need to go and fix that. And so we will have to see where magnesium is. Well, magnesium is actually the Q column, and so if I change that Z to a Q, we will hopefully have a good number. Okay, that looks pretty good. I'm going to then copy this over to calcium. And again, there's 1 mole of calcium oxide, and there's 1 mole of calcium per 1 mole of calcium oxide, so this 1/1 stays. And we need to change the R to what the value for calcium is, and calcium is U, so I will change that to a U. Okay, and then we have sodium, and now for sodium again, I'm going to pick the aluminum. And why am I doing this? Well, I'm picking the aluminum because, again, there are 2 moles of sodium per 1 mole of sodium oxide. So this 1/2 factor shows up again. And we have a value of 0. We see there's just a lot of sodium in here, so that obviously means I'm referencing the wrong column for sodium. So rather than W, let me go see what the correct sodium column is, and the correct sodium column is P. So I will change the W to a P. Okay, so we have our sodium value there, and then I'm going to copy this over for potassium. And wow, we have a big huge number there, but clearly there's no potassium, so again we must be referring to the wrong column. Potassium oxide is the same as sodium oxide in the sense that there are 2 potassiums per 1 potassium oxide, just as there are 2 sodiums per 1 sodium oxide. So let's fix the column. It is not Q, but rather it is T. And so we changed that, and you can see that potassium drops to 0 because indeed there is no potassium in this original analysis here. Okay. Fluorine is a really easy one because fluorine isn't calculated as an oxide, and so we're just going to refer back to the original fluorine value that we got in the element list. And so I'm just going to do equals, and I'm going to go all the way back to the very beginning and just pick the raw weight percent, not the moles, but the weight percent of fluorine, and that is going to be our value for fluorine. And again, to kind of pretty this up a little bit, I will make it 2 decimal places and center it so it looks the same as its neighbors here. So we've got 3 cells that we still need to take care of. We have an iron 3+ cell, we have an iron 2+ cell, and we have a calculated water cell. Okay, now keep in mind that all 3 of these are calculated because we didn't measure iron 2+ or iron 3+ or water, but they come out in the site fillings that we did. So let's start with the iron 3+ here. Again, I'm going to use the aluminum 3+ as the model because a lot of this equation is already built in here. So I'm going to move this over here. Okay, so that's a completely outrageous number. So we definitely need to do some fixing there. So this is based off of the iron 3 plus value. So what we want is we don't want this original iron, because this original iron represents all of the iron that's in the sample. So what we actually want is just the iron 3 plus here, so AH. Okay, so I'm going to change this to AH. But there's still a problem, and I'm going to sort of elaborate on this here in a moment. Okay, we get the right number, again, because there's no iron in this formula, but you recall that when I did all of these, I used the raw moles. Okay, I used the raw moles of silicon to calculate this. I used the raw moles of titanium, the raw moles of aluminum. But in this case, I have so far used the normalized moles. Well, we don't want to do that. Okay, so how do we get from normalized moles back to raw moles again? Well, what we need to do is we need to divide this by the normalization factor. So in the past, to get from raw moles to normalized moles, we multiplied by the normalization factor. To go backwards from normalized moles to raw moles, we need to divide. Okay, so I'm going to divide by the normalization factor. There we go. Okay, and again, I can put the $ in front here, but it's not really critical. And be careful not to put the $ in front of the 8, because we want this to be able to vary with the different rows that we have. Okay, so I hit return, and although the number hasn't changed, it really is now the correct number. Likewise, we'll do the same for iron 2 plus, and in this case, I'm going to use magnesium as the model. So I'm going to copy this over here. Again, we have the 1 over 1 because there is 1 iron atom per 1 FeO, but the P column is not the correct column here. And again, because this is a calculated iron 2, we don't want to go back to the raw iron number, but we actually want to go to the normalized iron 2 number. Okay, and then, oh, I've got an extra 8 in there. And then we want to, of course, convert this back from normalized moles into raw moles. And there we go. We have 0. So now we have all of the cations plus fluorine all worked out. So we have one last thing to do, and that is our H2O calculation. Okay. And H2O essentially works akin to the same way that Na2O or K2O work. And so I'm going to use this as the model, copy this over here, and now we have to figure out where are we getting the data for H2O. Okay, so clearly it's not going to be column V, so I'm going to get rid of this. And where we're going to, and actually I'm going to get rid of the 8 too, there. And I'm going to move over, and where we're going to get the data from is here in the OH column. So I'm going to click on that. And again, this is normalized OH. And so what we want is we want what the equivalent OH would be if it were not normalized. Okay, so again, we have to divide this by the normalization factor. And that would give us the equivalent OH that would be raw OH. Okay, and hopefully I've done this correctly. And we see we have a value of 2.2, which is a pretty reasonable value for the water content of an amphibole. Okay, so let's take a look at the subtotal. I'm going to add all of these together. In this case, I'm going to use the sum function because it's a little easier than just clicking on all of these cells. Just look at the whole lot here. There we go. Close the parentheses, and hopefully we're pretty close to 100. And yes, I have a value of 100. But we're not quite done here, okay? We have this additional column for which we call subtract oxygen equivalent to fluorine. Okay, now what this is, or what this represents, is that As you can see, we have a whole bunch of cations that are all oxides here, but you can imagine that if this were a fairly fluorine-rich amphibole, that some of those cations would not be bonded to oxygen, but would instead be bonded to fluorine. Okay, but we're assuming that all of the cations are bonded to oxygen when we do these oxide weights here. So we're clearly adding in a little bit of extra oxygen that really isn't there. And so we need to subtract that extra oxygen out. And the way that the subtraction is done, it's a fairly simple formula. It is a negative value, and so you start off with a negative sign there. And it is the weight of fluorine, okay? And we want to multiply this by the ratio of the molecular or the atomic weight of oxygen divided by 2 times the atomic weight of fluorine, because there are essentially 2 fluorines per 1 oxygen if you think about it on a charge basis, okay? And so rather than using the exact numbers, 15.9994 as the atomic weight of oxygen, I'm not going to worry about that level of precision. So I'm just going to round it to 16 divided by 2 times 19. And in this case, it should give me a value of 0 because, again, there's no fluorine. But you'll see that later on when we go to our fluorine-bearing unknown mystery amphibole down here, that not only will we have a value here for fluorine, but we will have a small negative number here that is subtracting out the apparent oxygen that's added to the oxide weight total. Okay, so finally here, we are going to do the total, which is just these 2 cells added together. And I can center this and bold it, make it look pretty, and there we have our complete amphibole analysis. Now I do have one final column here. It's called the name. If you take a look at my epidote spreadsheet, the video that goes through epidote, I have a little bit of a set of formulas that show how I go and calculate, for example, the end member. You could easily set up something like that. It's just a series of if statements where you take a look at at a paper like Hawthorne et al. 2012, if you want the most modern version. If you prefer the classic nomenclature scheme of Leakey et al. 1997 and its addendum in 2003, that will also give you good amphibole names, although technically not the most up-to-date names. You can either just simply look these things up in the papers and then type them, by hand here into the cell, or you can again have a series of if statements that do the calculations for you and then have the name just kind of magically appear there in the cell. But in this case, I'm just going to say catophorite because I know already that that is what the amphibole is. And indeed, we have finished with this first analysis. Okay, so I'm going to pause the video here for a moment. But when I come back, I'm going to copy some formulas down to these other amphiboles, and we're going to see how these different normalization schemes kind of play out. And hopefully I'll also discover that I have not made any math errors in here so that we can see that all the things are actually filled correctly. So let's take a pause here and then come back and check that out.